So thank you all for coming. Nice to see you, and thank you for participating. I'm Ella Riser from Tartu Biotechnology Park, and Tartu Biotechnology Park is working in the fields of biotechnology, medicine, and veterinary medicine. We're a business support organization and have also incubation program for biotechnology and medicine enterprises. We're participating in different international projects to evolve our working fields. One of them is Baltic Blue Biotechnology Alliance Plus project, which gathers experts, mentors, and cases in this field to evolve the blue biotechnology, which hopefully will help to lead to more diverse and sustainable economy. Today, we're holding the webinar of biopackages and circular economy. Why the topic of the package is relevant to enterprises is because plastic packages are a very efficient way to protect your product and its original properties. Unfortunately, with packaging to plastic packages, there entails a whole row of negative effects, like constant growing of landfills, trashing the environment around us, releasing toxic climate warming gases and so on. The fact that you are here today is showing that you are interested in finding a more environmentally friendly alternative for packaging. As the topic is diverse, then today we have presentations from different perspectives. The first presentation by Dr. Mait Kriipsalu is how the selection of packaging material contribute to circular economy, biodegradable alternatives. In his presentation, you will get overview of different plastics and their properties, which is environmentally friendly, which not. In second presentation, we'll talk Fredrik Gröndahl about Swedish strategical project for a bio-based economy, sea farm, working with cultivated kelp as the biomass for food, feed, and bio-based materials. With the talk today focused on the use of bio-based materials. In the third presentation, Tõnis Paara will give a short overview of different bio-based and eco-friendly packaging solutions, properties, price, and availability on the market. Also, he introduces the reality of biodegradable materials and insight to prospects of eco-friendly packaging. Mait Kriipsalu, who is giving our first presentation, has been working in Estonian University of Life Sciences, Chair of Rural Building and Water Management for 26 years. He has been working on different positions, including professor, focused on water and wastewater treatment, solid waste management, and biotreatment of organic waste. He has been cooperating with Estonian Circular Economy Industries Association and the Certification Center of Recycled Materials. Being a board member and vice chairman of European Compost Network, he has contributed in development of Estonian end of waste regulation for bio-waste compost. Now I would give the word to Dr. Mait Kriipsalu.
So good morning, everyone. When deciding upon the topic, I wanted to share some of the worries that I have about packaging waste and also about new packaging material. So let us walk through the biodegradable alternative issue. So why do we talk about biodegradable packaging or plastic at the first place? It is simple. We are worried about littering a lot. So here you see a picture of a forest, but you don't see those 100 trees and bushes. You see a lot of plastic in the nature, and we don't like it. And we believe that biodegradable plastic will save our nature. And is that false or true? That is a tricky question. First of all, we have a mess with definitions and words. While scanning terminology in internet, you hit words like biobased, bioplastic, degradable, biodegradable, compostable, and it is kind of messy. How do we sort out here? We are worried about oil. This is one of the reason why we talk about bioplastic or biodegradable plastic or bio-based. Or we are worried about littering. They are two fundamentally different worries. First place, we know that we might run out of fossil oil in some future. So we would like to replace crude oil in plastic industry with some renewable materials. And this is our first worry. Then we are worried about littering. And we wish that plastic disappears by itself, so-called out of sight. And this is so convenient. It's so lovely if it happens. And we try to fool ourselves a little bit by replacing conventional fossil-made plastic. What we need to know about that is that plastic can be non-degradable and it can be degradable if we play some tricks. Plastic can be bio-based or plant-based, and plastic can be fossil. And on this matrix, we have 4 options. We have either fossil-based plastic, which means it will not degrade, and we want this way. For instance, the furniture that we have made of plastic, we don't want it disappearing. We want it stable and long-lasting. At the same time, this plastic is made of fossil, and we would like to have replaced it with a plant-based material. And this plastic will not degrade, and this is okay, because we don't want that our furniture or windows or doors disappear. If we talk about single-use plastic or consumer plastic, then the best would be if it is bio-based and it will degrade or it will compost. So this is what we love. And there is a 4th option, that plastic is made of fossil raw material and it will degrade somehow. And I put it like maybe, because this is the most tricky. We will come back to that. So we have 4 options. We talk about biodegradable, but I don't really like this definition, because it will give you no hint about what will happen to this material in the future. If we talk about compostable, then we understand that we wish to have this material in our compost heap, and then we wish that it degrades, according to theory, into CO2, water, and bacterial biomass. And this degradation is done by activity of bacteria, which is lovely. And this is a copy of any natural processes which are happening in our nature. Is it biodegradable or compostable? That biological degradation takes place in our compost heap, but also in water and soil. But if we talk about waste management, then we don't talk about putting waste into soil or putting waste into water, but we do talk about composting, putting waste in a compost heap. That's why, from a technical point of view, it's more correct to talk about compostable plastic and composting our plastic residues in the context of this presentation. So the theory tells us that plastic, biodegradable plastic will degrade. And this is very often illustrated by pictures like this. You have a cup. After a couple of weeks, it starts to degrade. 1 month later, it is nearly nothing. And in the end, it becomes a part of nature. And this is very lovely. And we would love to have it. But this is partly true only. It is, yes, it is positive if it happens in controlled environment. And this will never happen if this environment is wrong. To illustrate, this plastic cup will not degrade on our table. It will stay a plastic cup on our table, but it will degrade in our compost heap. So the environment is important. The philosophy of composting, compostable plastic, is that we want to compost it together with organic waste, not alone. So the objective is important. We want to degrade our food waste first place. So to illustrate, we take our food waste, we collect it in our compostable plastic bag, and this is what we want. The false objective would be degradation, would be a wish to degrade pure bioplastic. Take just a little bit of food waste, wrap it in a very big heap of compostable plastic, and the result will be very bad. I see this kind of a wish or wishful thinking, for instance, when organizing our festivals right now in Estonia, where the organizers try to replace plastic cups and plates and forks with biodegradable, and then they collect it, and then they expect that now we should degrade it somehow. But it is a big heap of plastic, clean, quite clean plastic, and degradation will not happen. So, what does it mean, degrades or composts? It is written that it degrades under controlled composting conditions. So we need to know what are those conditions that makes degradable plastic to degrade. We have a standard 13432, which tells us that we can consider plastic degradable or compostable if we put it in industrial composting process, which means that we guarantee that there is enough oxygen, moisture, temperature, pH, so the environment has to be correct. The degradation has to happen during reasonable time. So we require 90% of degradation during 90 days. And we wish that it degrades well, so that no more than 10% of input material after this 90 days is more than 2 millimeter large. So what is industrial composting process, and how does it differ from composting that takes place in your backyard? You know that for composting there has to be enough temperature, oxygen, moisture, time, and mixing. So it's a volume based, and we need some technology to help to move and lift those large masses of waste. At home you have just a couple of 100 kilos. To understand the meaning of control process, I am showing you the picture of a professional composting site and the professional composting heap. And the other picture is about your home composting options. There are two composting devices, and the big question is, do you have controlled conditions here in both of those pictures? For instance, take the industrial composting process. You see a certain line here. On one side of the line, condition is different than the other side of the line. So I don't see really that the composting company has a full control over what is happening in this compost heap. In one place it is too dry, in the other place it is too wet. And the plastic that ends up in either side of this line acts differently. So it is very difficult to imagine that any type of compostable plastic, be it so perfect, it degrades. In your home composter, do you have composting conditions good enough to facilitate degradation here? In this open composting device, no chance. And in this closed composting composter, we don't see what is inside. If it's half empty, no chance. So it is difficult to facilitate those composting conditions firsthand. Does my bioplastic or compostable plastic degrade in reality? As told before, the result is depending on the environment into which it is exposed. So we can adjust our composting by shredding any type of input waste into smaller particles, which helps, which will happen in large composting facility, but nearly never at home. We mix and blend compost. Sometimes we mix the windrows daily, or maybe in the beginning of the composting process, twice per day even. At home, we rarely mix and blend our composts. We adjust CN ratio, we add water and air in a composting facility. That's why we talk about industrial composting. I have heard statements like this cup or spoon or bag degrades in 2 to 5 years. And I am convinced that the statement is deeply wrong, because this statement sounds for me as do nothing. And this is never ever a technology. Imagine you propose a new material on the market, new magic material that replaces plastic packaging. How do we get a proof of quality? How do we learn that this material is truly okay? Before going to the example, I would like to give another example about our virus situation right now. We all talk about masks, don't we? And suddenly we talk about fake masks. Have you noticed that? Fake means that this mask may be made of wrong materials, maybe of wrong design, or maybe coming from wrong production. Wrong material means it does not make the job. Wrong design means mask may be good, but air comes into holes or openings elsewhere, so it doesn't make the purpose. And wrong production means sterile mask made in unsterile factories, which is also very wrong. Or we are unable to prove certificates. I, as a producer, cannot tell that this material is perfect. I need to certify it so that independent body proves that my sentences and statements are correct. And then we see the headings. They are all headings from newspapers. That fake mask flood markets, which means money talks. If you produce a perfect replacement material for plastic, someone produces a fake material and floods the market. And it can also be that you produce a brilliant mask, but you use it incorrect. As explained on this picture, you see a person, sorry to say, sick, taken to the hospital by 2 professionals, and you see how wrong those 3 people, 2 of them professionals, they use a mask. And the message of this talk is that we need to avoid similar mistakes while replacing plastic packaging with the new packaging materials. So we need to make it from correct materials, correct design. We need to have a good certificates, and we need to use and dispose material correctly. Back to the compost. We have a standard which tells how do we understand that material is biodegradable. But this is not enough. We need to test that this material is compostable under certain conditions. So we need to have a field test. It is not realistic that every country, every city, every family will make a test by themselves. We believe into testing facilities, and we have a couple of or few such testing schemes in the world. In Europe, one of the best known is OK Compost, which makes experiments, and if the statement is correct, they print a logo on a new plastic materials, stating here that this compostable plastic is compostable in industrial composting process. The next one tells that it is compostable in your home composter, meaning that it's very thin and rarely degrades in conditions that you have at the home, or it is degradable in soil. Degradable but not compostable. So you put it in soil as like plastic from strawberry production. You don't collect and compost in heap. You put it in soil and then it degrades. So we believe such standards and testings, and sometimes those logos also state that this is, for instance, bio-based, made of plants, not from strange input materials. In some countries, the logos are different. In US, for instance, the common logo is here. In some countries, it can be different, but the meaning is exactly the same in every logo. Someone has tried and succeeded composting this material in a compost process. So back to that, you have basically you have two proving options to try to find the logo on a material and try to find the standard on a material. But there are also alternative materials on the market. For instance, I have picked a sentence telling that there are materials that decompose. However, they do not decompose, but they decompose, which is very much confusing, because there are 3 times where they use the word decompose, and every time the meaning of this word is different. And this is so wrong. This is not composting if material decomposes into fragments, into small pieces, into microplastic fragments. This is a game of words or wishful thinking or half-truths or unfinished sentences or just fooling the customer. This type of plastic is called oxo-degradable. Oxo-degradable plastic indeed degrades into pieces, but it will not degrade with the help of microorganisms, so it is not biodegradable. Does it help us? Does it help to replace plastic with oxo-degradable so that we get out of sight, so that we get rid of littering and it happens by itself? I don't think so. First, we need to understand what is oxo. What is happening there? In oxo-degradable plastic, we take fossil-based plastic like polyethylene. We put some compounds in it that support breaking into pieces. What are those compounds? If you Google, you find different options, but usually those are salts. Salts of iron, manganese, nickel, cobalt, and suddenly you understand that you add heavy metals into plastic to get rid of plastic and to put heavy metals in our environment, and this is wrong. Why does it fragment? It is not because of microorganisms firsthand. It's more like because salts are catalysts sometimes oxygen and UV radiation accelerate the process. Is this compostable plastic or not? What do you think? I have made a picture here in Estonia where it is where green park waste is collected into so-called biodegradable plastic bags. I don't think that it is biodegradable because I see no logos, no indication that they are biodegradable. And a couple of years later, I still meet the same bags in a compost heap in a professional compost facility, and this plastic has not degraded, not at all. So this is not degradable or neither compostable. This is a fake oxo-degradable bag. And what happened really is that we took the best possible organic material, in our case green waste, and we contaminated it with plastic. And this is so wrong. Is plastic containing compost possible to certify? If we talk about quality, we need to have a certificate which indicates the quality. Here in Estonia, we have a end of waste regulation that gives you the way how you can market the compost under the name of product. And in this regulation, it is stated that compost may be produced only from materials that are listed in Annex 1. And this annex, it is stated that bioplastic is okay, but only if it is carrying a logo or proving that it is produced under the standard 13432. So now you have two options. You have to prove that any plastic that is in your compost heap is according to the standard. And the answer can be yes or no. If this answer is no, then no chance. You can't you can't certify your compost. And if the answer is yes, then you have to prove another thing. You have to prove that there is not too much of it. So you have to prove that it is under 5%. Otherwise, you have to tell the customer that this compost is made of plastic, and you guess the marketing will collapse after this sentence. So better avoid. What is the future for oxo-degradable plastic? When they arrived the market, they made a massive campaign of marketing, and it seems that it is good. But after studies, after massive studies, the conclusion was that there is no evidence that it is beneficial, and there is no evidence that it is biodegradable in reasonable time in open environment, landfills or marine environment. And the future is that this type of plastic, luckily, will be restricted in EU since next year under the ban of single-use plastics. So we can conclude that we will get rid of one problem child. But is genuine compostable plastic okay? So we have some food waste, we put it in plastic bag, and then plastic bag goes into the brown bin. This is the way how things work in Europe in most countries. Is it okay? If you look at this picture, the single one thing that we notice is that there is a lot of plastic, be it genuinely compostable or not. In any case, there is a lot. So we use a lining bag to increase the amount. We use the lining bag to make collection clean, but we increase the amount of plastic in the compost. And this lining bag It's very expensive, large size, and it may cost €1 or even more. Why do we need this lining? We want to keep everything clean, but do we have any alternatives? Maybe we should wash these bins now and then instead. So try to not stop your way of acting with just one option possible. Is lining necessary? I tried to illustrate with photos here that this bin is only for bio-waste. This bin is not lined, and we see here food waste, which is put perfectly in compostable bags. Everything is clean and nice. And here we see the picture of a bin that is lined with a perfect compostable bag, and food waste that is put in this bin is put in regular black plastic bag. So this is what we want to avoid. It is not a plastic bag that we should blame. It is people, it is us that act wrong. The role of bioplastic. Why do we need this type of plastic, compostable plastic? First of all, people love it because it makes it clean to collect organics. Secondly, companies love it. Waste companies love it because it seems that there is no need to react or screen out plastic during composting process. Does it work? People make mistakes. As soon as you allow compostable plastic, some people put also wrong plastic. You need to sieve it out anyway. There is a tendency that we overload, that we sort of overkill. Too much compostable plastic is never good. And our waste company, our good colleagues from waste companies, they tell that some people pack every single food waste piece individually in plastic, compostable plastic bag, and then they put it in a bin in a with a compostable plastic lining. So we need to tell people, don't use too much plastic. And also, everything must fit with the rhythm of composting, because composting takes time and there are certain steps. And if this plastic is too much, then it doesn't work. The reality is like this. This picture comes from a composting site from Tartu, where I live. And what do you see? You see here a lot of plastic, right? Is it okay or is it not? If I indicate some of the items that I don't love, there is a lot of plastic. But is it a panic situation? Some of this plastic may be compostable, and then it is okay. So do the composting facilities accept compostable plastic? We need to ask from them. We haven't, but our good colleagues from CIC, the Italian Compost Association, they have made a study recently, and they have asked from biogas production, from biogas plus composting facility, and the genuine composting facility, if they accept 3D plastic, which are bottles and cans and pots, and if they love 2D plastic, which is foil. And the answer was like this. Can you predict? The answer was like this: no, 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 and yes. So we produce biodegradable and compostable plastic, believing that composting facilities love it, but they don't. What's the reason? Why? Why do they say no? It's very simple reason. Plastic just disturbs them. Even if it degrades, it still disturbs them. Problem. So we wish to have this kind of picture. This cup degrades in composting environment during 90 days. But anaerobic treatment, biogas production has different wishes. If it is a wet process, they want the material to be pumpable and mixable, and plastic kills pumps and mixers. If the biogas production is dry, then maybe this is not an issue. But both dry or wet, biogas production is done during 3 weeks. Too short. There is not time enough that this plastic degrades. So this is place where everything is wrong. And the biggest mistake is that biogas production is totally anaerobic, but biodegradable plastic is degraded under aerobic conditions. If we use composting, usually it is done in less than 90 days. And this plastic also blocks the gas flow. Oxygen cannot get in and CO2 cannot get out if there is too much. So simple is that. So back to this plastic heap, we need to have lifelong learning. I have picked 2 items here. The first is this, our favorite rucola pot. The message actually goes to the producer of this material or this pot. And the message is like this: dear manufacturer, please redesign your product. Replace the plastic pot with a paper or peat or other compostable alternative, and replace the polyethylene foil with a biodegradable, because this is the way how people dispose this material after using. And then there is another, our favorite item, which is a pot of ketchup. And we should teach customer here. Dear customer, please change your habits. Empty the package and separate this package as packaging waste, not bio waste. Who does this teaching? Is it a local authority, waste company? We need to agree upon the teaching duties. If we put plastic in our compost heap, it will get into smaller pieces, smaller and smaller. And this is what we call impurities. And this is what we call microplastic. Here is a picture that I took here in Estonia, and probably you notice impurities, right? Do you notice? Do you think there is a lot? Just by watching, it's kind of difficult to judge, but I zoomed in and I have marked items that I don't like, and this is this much that I found just by watching. And now there is a big question: would you personally accept this compost in your personal garden? And I already know your answer. It is no. So that is why we don't want plastic in our bio waste, and that is why we need full degradation of your compostable plastic if we go for that. I have put another photo here that I got yesterday. I got a photo from a compost company in Estonia with a positive message. Look, we have made a good quality compost. But what I did, I manipulated this picture and I turned it black. I took out a fragment, zoomed in, and turned it black. And you see, so you see the sky with the stars. Every star in this black compost is an impurity, most likely. And this is what we want to avoid. Back to the bio-based. The raw material for bio-based plastic, wishing to replace fossil fuel, should be, for over the many years of testing, has been typically corn or wheat or rice or rye, something like that, that grows. And this is a typical advertising that you see from internet. And it has a big ethical problem because this is what we eat. We should not use edible material for producing bio-based plastic. Instead, we should use non-edible, be it waste or byproduct or residue based. And the better case, the material should have a negative carbon footprint, so it should capture carbon while we grow it. Try to know that. Compostable plastic and circular economy. What's the link? When replacing fossil-based plastic with a compostable, first question you should ask, does it have to be plastic first place? Maybe wood or paper or board-based plant-based packaging fits better. So ask this question from yourself. And then when making decisions to introduce a plant-based plastics, try to guess, how do we separate it later after using it? And how do we recycle or recover, or how do we dispose it? It's a very big question. Usually, we put our waste in brown bin if it is bio-waste. We put it in yellow bin if it is a packaging waste, or black or green bin if it is residual waste. We wish to have, we accept small amount of compostable plastic in our brown bin, but we get large amounts that we don't like. We don't want to have any compostable plastic in our yellow bin, but we get. And we really don't want to have compostable plastic in our black bin, but we get. So, did you make the life of waste company easier or more complicated? A very big question. How do you recommend to treat your bio packaging, bio or compostable packaging? Should we put it in a landfill? The answer is no. We don't want it in a landfill. And European waste, the future of European waste tells you that you can put only 10% of waste in a landfill that we used to do it so far. Incineration. We really don't want to incinerate your bio-based plastic, but it is okay, it burns. Or we don't want to put it in a cement kiln as a waste solid recovered fuel or refuse-derived fuel, but it is okay if we do. Composting would be the best, and biogas production would be not brilliant idea. And direct recycling is just not working, or if it is working, then the collection system for only bio-based and compostable plastic is not working. To the conclusion, just a couple of examples. Should we replace this packaging with a biodegradable compostable? And I would say no. This is perfectly recyclable as plastic. So collect it separately, recycle as plastic. Should we replace this? And the reply would be quite yes. First question, can we do without packaging firsthand? If not, then maybe we should try to replace the tray or the base with a paper instead of plastic, and the foil, it is quite okay if it is compostable then. Should we replace this with biodegradable? And the reply is no, no, no. This kind of packaging must disappear from our market because it is very, very wrong. What about this? I would say yes. This packaging is dirty with food or soil anyway, so try to replace it with a compostable. From soil to soil, we should support composting because nutrients, organic carbon, and microbes should go back to soil, and we should target complete degradation under controlled environment in our composting facility. We should try to reduce fossil-based plastic, but to use only material which are not edible So feed the planet and try to produce plastic from sludges instead of food stuff. And if we use this kind of material, try to reduce using this plastic or single-use plastic to maximum. Reduce it. And when marketing your alternative packaging materials, please try to indicate us how do you as a producer or a selling person for this material, how do you recommend to recycle it? Otherwise, you will confuse the society. So the purpose of using compostable thin bag is very good. We need to facilitate collection and recycling of organic waste. Do it. Thank you.
Okay, thank you very much. So we only had one question. What are the main points of the presentation? What we should bring it from here?
The main point, I was thinking about this question before, and the main point actually comes in a combination of next presentations.
Okay, very good.
The main point is that whatever the packaging material, reconsider the packaging material, try to use compostable materials, but minimize the amount. And be sure that if it is compostable, then it ends up in a composting system.
Okay, thank you very much. And now we have a second presentation from Dr. Fredrik Gröndahl, whose background is in oceanography, chemistry, and marine biology. But for nearly 30 years, he has been working with engineers at KTH and the Swedish industry, with a focus on environmental effects and sustainable development. He's an associate professor in industrial ecology. So the floor is yours, Fredrik.
Could work like this. Well, that's super nice. Thank you. Okay, my name is Fredrik Gröndahl, and I work at KTH at the Royal Institute of Technology in Stockholm, Sweden. And I have, as you said, for many years been working with algae in a biorefinery concept. And today we will talk a bit about algae-based materials. And it's actually, I am the project leader for the whole Sea Farm project, but Martin, that is also a part of this presentation here, and he's also in the audience. He's the expert on bio-based materials. And if you have tricky questions, he's the one answering those ones. So I will just take you through the Sea Farm project and present some pictures. From the beginning, we were thinking about sharing this presentation, but it was a bit too technical, difficult for me to see how that would go. Anyway, so let's start. And I always like to start with this picture. This is actually the European Union strategy for a long-term sustainable development. And as you know, in 2009, we had a financial crisis, and then there was a budget that the European Union presented that was very work-oriented. And that meant that in the coming years, there would be big investments in research and development that could generate new jobs and in industry and create new jobs. And a very more applied research budget, you could say, in that sense. And there was also a discussion that land is actually being overutilized. I mean, the former presenter here talked about the raw materials that for bioplastics that come from corn, for example. This is, of course, problematic because land is very close to the carrying capacity. How much could we sustain on land production? And it seems to be impossible, I would say, for the future when we have a growing population to also cultivate energy crops or crops for bio-based materials on land. because we need the land ecosystems, or the agricultural land at least, to produce food for humans primarily. So then we have to start to look in other areas. We always have forests, for examples, and forests are important and will be very important. But we also have a very big part of our planet, and the big part of our planet is the sea, that constitute about 71% of the total area of our old planet. And the sea we have been not so good on utilizing. We have gone out at sea and been fishing in a very voracious way, taking up predatory fish very far up in the trophical pyramid. I mean, there are tuna fish, cod, and fish like that are top predators that we have been fishing and eating. Salmon is another example. We have been cultivating some fish in the oceans, but we have also used a lot of chemicals and antibiotics and things like that. So that is not that sustainable either. So we need to use what we have been doing in the sea. We have to do it in a better way, but we also have to unlock the big potentials of the seas and oceans. And if you just take an example on land, one species now, the humans, are using about 45% of the net primary production just to feed ourselves and our cattle and all the animals that we are keeping in close to us that we are using. But in the sea, we are utilizing less than 1% of the primary production. And there you could see there is a very big potential of using the sea in an efficient way. And that you could do in many ways. I mean, you could have more energy systems out at the sea, wind farms and wave farms and things like that. But you could also start to cultivate the sea, increase aquaculture. And this especially in the North Atlantic area. I mean, in Asia, Japan, China, Korea, they have been doing this for a very long time. But in the North Atlantic, this is relatively new. And now there is a lot of initiatives starting to produce mussels, fish, etc. in the sea. But what we have been doing is to produce seaweeds. And seaweeds or kelp or algae, macroalgae, are the forests of the sea. And here we have a huge potential of creating a bio-based material, a bio-based substrate that could be an important part to replace the fossil based things that we have been using for a long time. So that was a short introduction. And what have we been doing then? Yes, we have been working in the Sea Farm project. That is a strategical project for a bio-based economy that have been financed by the Swedish Research Council for Sustainability and Agriculture. And this have been a 5-year project. It ends now in the summer, but we have also a number of spin-off projects from this algae research with a number of other very big projects actually, both on a European Union level, but also on a national level in Sweden. The idea here is to produce a brown algae, or at least in the sea, sugar kelp, Saccharina latissima, and finger kelp, Laminaria digitata, and a number of red algae and green algae that we cultivate mainly on land actually. These algae, we want to use them for a number of different applications in the Sea Farm project. We have been studying how we could preserve the biomass and in which way we should preserve it, and it depends also on the usage of the biomass. Then we have been focusing very much in the biorefinery, what to do with it. Some of it is eaten actually as it is, the whole algae could be eaten, and that is very popular now. So a large proportion of the algae that is cultivated in the world is actually for food. But you could use it as feed also. But you could also take in the biomass into a biorefinery. And in the biorefinery, you could degrade it, into different fractions. You could create interesting feed stocks that could be used like fish feed or feed for chickens or cattle, etc. You could create new interesting bio-based materials that we will come back to very soon, what we could do with algae as a material. Interesting things could come out from that. But you could also extract energy. The algae are very rich in carbohydrates, sugars, so you could create ethanol, or you could create decompose it and get methane out of it and create biogas. So there is also potential for the energy production from algae. The best thing is if you could do everything in an integrated biorefinery where you utilizes all, I mean, you have a process chain where you create a value in each step of that chain. And that could be the best strategy in a high-cost country like in Sweden or Norway, for example. Anyway, the project started with experiments how to cultivate these algae. No one have ever done that before in Swedish water, or not much at all in the North Atlantic. So simultaneously here, there were initiatives in different parts of the North Atlantic, in Denmark, Sweden, Faroe Islands, Norway, now in Canada, the US, and so on. And more or less started experiments with these cultivations. Something that turned up here that was a good success in our project was that it actually worked very well in Swedish waters, especially on the Atlantic side, where we have a bit higher salinity and also a nutrient-rich currents transporting nutrients from the Baltic Sea to the west coast, and that means that these algae are growing very fast. When we deploy these algae into the water, we cultivate them on ropes. We do, they are very small, a few millimeters when we put them out at sea. And then after about 5 to 6 months, they are 3 meters in size. And you could literally see these algae growing. They are like a bamboo. They grow very, very fast. So there is a very big potential in growing huge amounts of algae on the ropes. And that was a surprise. Suddenly, the Swedish water, due to the eutrophication, the overload of nutrients we have in our coastal water, it was really a very good production. Well, in comparison with Norway, that always have much better waters actually for aquaculture than we have, or in Denmark or other places. So that was good. So what we could do is we could produce algae in Swedish waters. We could do this on ropes. We could produce this brown algae kelp. They have a high yield that is very nice. We could do it in a very sustainable way because we don't need to put any fertilizers there because the sea itself fertilizes the cultivation. We don't compete with arable land or agriculture on land, so we don't have this competition with the land agriculture and the food production on land, and that is a big advantage. And of course, at least in Sweden, but I think also in Estonia and other parts, we have had some very hot summers and we have a climate change, and water shortage is also a problem even on our latitudes. We normally don't have that in Sweden, but we had it a couple of years ago, and that means that these plants we don't need to irrigate, and that is also a very nice advantage. It's work intensive when we deploy it, but then we just leave them there for 5-6 months, and we just harvest our yearly harvest right now actually, and then there is working efforts, but in between that they just handle themselves and grow nicely in the sea. Okay, here we go. Since the focus today was material and material design, we have this biorefinery part of the project, and the biomass goes into the biorefinery, and the biorefinery is in this case at the Royal Institute of Technology, KTH, and it's at the polymer chemistry lab there. And there, Martin and other colleagues take care of this biomass and fractionate it into proteins, lipids, other chemicals, polymers, fuels, and so on. Look on the characteristics and the possible ways that could be used. And then in the Sea Farm project, we have been looking on to produce, at least demonstrate materials that could be done by algae or from algae. Some parts of this are very, like proteins and the lipids, are very rich. I mean, the proteins contain all the amino acids that we need as human beings. The lipids the same. They are these valuable lipids, omega-3 lipids that we also need. And they could go to Chalmers in this case, that is the other technical university that work with food technology. And there they could invent nutritional bars, food, and enrich food with things from the algae. Anyway, we stay at KTH and see what could be done there with from a material point of view. And in this case, we have also been cooperating with the Aalto University in Helsinki or in Finland, and there just to see the possibilities of using algae also as art and sculpture and different kind of material. So this is just from the design museum that was in Helsinki, the exhibition. And we had this workshop at Kristineberg, that is a marine station on the Swedish west coast. And this was like a creative workshop where we did all kind of things with algae. We did different types of material together with polymer chemists such as Martin. We did food together with the students. We were eating the algae. And then we had the design students from Aalto that did art, lamps, and materials. We even did clothes and textiles from the algae. So there is a huge potential of using algae for many things. And that makes these sea forests very important and potentially very important for a future sustainable industry. This is other examples that I've just taken a few pictures for showing. This is like insulation. This is a tradition. They take the beach cast, the algae from the shore. Some areas are very rich on this. In the Baltic Sea, we have rich areas on the island of Gotland, for example. There is also in the south coast of Sweden. We have it in Danish coasts. There is a lot of algae that is swept up on the beaches, and they could be collected. This has been a long tradition of this, for example, in Denmark, but now it's taking new turns and being a part of developing old tradition that is being reused here as a environmental friendly insulation. But you could also do other things with this material that have been on the beaches, the beach cast. There are other things that we actually have tested a little bit also here in Sweden, and that is to make bricks where you mix the algae. In this case, you could do it with sand, for example. This is from Australia, where they do a very long-lasting, resistant bricks that are completely comparable with bricks from traditional bricks. And here they use also sheep, and they mix the fur from the sheep together with the algae and create a long-lasting material that could be used as a building material. In this case, if we use the algae in this case, they will be locked for a very long time into a construction. And when that is done, we will also trap the carbon dioxide that the algae have been capturing from the sea and ultimately from the atmosphere. So this will actually turn into a carbon dioxide sink. And this material could last for hundreds of years, and then the carbon dioxide is taken away from the circulation. And in this way, depending on what you do with the material and what kind of material you do, you could trap carbon dioxide. Another advantage, of course, is that you take up the nitrogen and phosphorus when you harvest the algae, and in that way you also take part in reducing the eutrophication in coastal areas. Okay, now we come into more of these specialities here, that and if you have the real tricky question, you could send it out in the chat here and Martin will answer. But this is just to show a little bit where we have two types of algae. We have the macroalgae and we have the microalgae. The macroalgae is what we cultivate in the sea farm project. Microalgae, you need to cultivate them in bioreactors, and you do that mainly on land. And there are more bottlenecks in cultivating microalgae. But on the other hand, microalgae could produce many valuable things. In this case, one example is a type of polyester thing, PHA here, that could be used for clothes, for example, and also polyethylene, ethylene gas that the plants and algae produce that could also be polymerized to a plastic. But as the former speaker said, when you create a plastic, even if you do it from algae, it will turn into a real plastic. And then you have the trouble also connected with plastics. So a plastic is always a plastic, you could say, and even whatever material it's done from. The only thing you could say is that it might be more environmental friendly because it's not from a fossil source. In that sense, it's good, but you have the degradable problems and things like that you have with other plastics, also from potato starch or something like that. Anyway, then we have the macroalgae that we are cultivating, and there you could have polysaccharides. They are very carbohydrate rich, and there you could get the alginate from brown algae, and we will discuss that a little bit more, what you could do with the alginate, because if you use the alginate as a, in a similar way as a plastic, you could say, you will actually have something that is really degradable and that will turn into a carbon dioxide and water eventually, and that is environmental and sustainable. We have carrageen from red algae that you could extract, and agar from red algae. I just heard, I read a paper yesterday about just carrageen from red algae, that a research group have worked with a coating that could prevent virus from attaching to different material. So this is part of this corona discussion that is now. And I was so happy that I found an article where algae could also save us from corona. So that is an interesting thing. They actually put it as a coating material on different things, and that eventually makes the virus not possible for the virus to attach to the material and spread in that way. Okay, here's another little picture here showing different ways. You have the polysaccharides here. They are biodegradable, as I already said, and they are energy efficient to recover. And the PAH from the microalgae we mentioned are both biodegradable and melt processable. And then the polyethylene from microalgae is also processable, more like a plastic. Well, this is how the brown algae, we focus on that. I mean, in the sea farm project, we have mainly worked with the brown algae, and in other spin-off projects from sea farm, we have been dealing with the green algae and red algae. But here we have one of these sugar kelps, then Saccharina latissima. And in different, the there are in the different layers in the plant, you could say, in the algae thallus here, you could find different things. So in the cell, you will find mannitol, laminarin, for example, that could be valuable. And then inside, you could also find cellulose, alginate, fucurine, and so on. So in different layers in the cell wall, for example, you find that. So there are in different parts of the body of the algae, you will find different types of material, and you have to be aware of that. And especially in the cell wall, that is very rich, you have to find ways of breaking down the cell wall in an efficient way. Of course, you could use very hard chemicals here that are not that environmental friendly, but in the sea farm, we have been working with green chemistry and want to use as smooth ways as possible and as sustainable ways as possible when we do this breakdown. Especially the cell wall could be difficult to break down. Yeah, this is just showing a little bit about one of these polysaccharides and some of the construction here with calcium that is involved. Then you could do alginate here in different ways, and there are some comparisons here that we will look into soon. This is something that Martin has been doing in his PhD, and he has been working on the extraction of alginate. And he has, since we already said here, we wanted to have as environmental friendly extraction methods as possible. We could see he have been using sodium citrate in a way here, and the blue color here show how efficient it is actually in, and he's doing it in several cycles. He could extract this quite efficiently, and that means that it's a very good method, and this method is also published. You could compare it here with water. You don't get much out of it, or sodium acetate or other extraction methods here. So it seems to be a quite good way of doing this in a environmental friendly way. So this is what is been doing. We have the brown algae. It will be dried. It goes into the biorefinery in that sense, in that way, and then it will be chopped to pieces here, and you will have calcium ions there. And you have this multiple extraction cycle, and you get out this alginate there eventually. That could be used for interesting things. Yeah, I will not go into this. It's more if you're interested in this extraction cycles. These are just showing the different concentration of the sodium citrate and how efficient it is. You could send a little question to Martin. He will explain it more for you. Yeah, so now we come into what we actually could do with this alginate that we are focusing a little bit now. Martin is now a postdoc on this, and he's doing a lot of experiments with the alginate. For example, doing a spinning of a thread, it gets like a, you could call it the plastic spaghetti or alginate spaghetti, and then you could test the strengths of this by putting a weight there. And we are trying here to find as strong as possible, creating this thread that could be used for many things. Yeah, this is also in the wet stage here. I will not talk so much about this. It's more the stress of it. Here it's compared with a more traditional alginate, and you could see, I don't see the figures myself here, so that's, yeah, I skipped that one. Here is with the calcium and with aluminium, just showing that aluminium is not that good, I guess, and that shows that the calcium works very well, and it has a high drawing stress, and it works good, and it's well comparable with the commercial alginates that you could buy. So that is good. And then finally here, we could mention a little bit what we are doing now, developing this knowledge that have been gained through the research from Martin. And here is just an example of the spinning that I showed before with the thread, but also how to use the alginate for cups. And as you know, there is a lot of usage of plastic cups and other plastic materials. And now we have started a project a little bit where we are looking into replacing, in those circumstances when you just need a plastic cup for a very relatively short while and for one-time usage. I could be just having a drink of water or something like that, and then you throw it away. This could be a way of doing it, because here you will get a real nice degradable cup that could be actually you could actually eat it, I would say, or you could just throw it away and it will degrade into carbon dioxide and water eventually, without the harmful micro fragments that a plastic would generate when it's being degradable. So this could be something that could be done, and we are looking into that and see how this could be used in different usage. There are many plastic cups are used in the society. I mean, we just took an example from the Swedish dental industry that actually 50 million cups are used every year in Sweden. And in this case, it might be a good idea to see if this could be replaced by these alginate cups. And we are actually doing some experiments with this, and we are going to test it in some dental clinics and see how customers looks at it and so on. Of course, this production of these cups will be more expensive than the traditional plastic cups, but on the other hand, it's a relatively low cost if you compare it to a visit to the dentist, for example. So it might be a way of doing it. We will see how this work continues, but this is just to give you a little bit of an idea about what we are doing. We are also looking into other materials and we have a lot of ideas about how we will develop this in the future. But that is for another talk, another time, and we have a lot of research and development on this. So with that, I would like to, thank you for the attention. It's very difficult to talk with your own screen like this, but I hope I went through a little bit at least. Thank you very much for this.
Thank you for your presentation. It was very interesting. Do we have some questions already here in the Q&A?
And don't forget that Martin is there. He could give you all the chemical difficult question. He will answer. Eller hur, Martin?
Absolutely, absolutely.
And I'm also here and happy to answer some more of the more general questions on commercialization, sustainability aspects, and so on, if that's of interest.
We have Jean-Baptiste research group. Good.
I have a question for you also. Are you also providing materials for enterprises who would like to use the plastic you're producing?
I mean, if you mean the raw material, algae in itself, or
plastic? I meant plastic from algae.
Yeah, I mean, we haven't started yet to. I mean, we are still doing. I mean, we are in the stage actually that this will develop into we have a spin-off company that have just started, and we will see how it develops in the future. But right now it's only at the university and the university lab when we are doing this. We are not selling this material yet.
Okay, maybe in the future.
Exactly, definitely.
Yeah, maybe Fredrik, I take the opportunity to ask you directly via the phone here now. So very interesting presentation. First of all, thank you very much also for organizing this webinar. And quick question about the polyesters you're deriving. Would these polyesters be able to be used also in lamination adhesives?
So I can take that one.
Martin takes it.
So these polyesters is nothing that we are producing ourselves. It was an example of what you can get from microalgae, but they are melt processable, and could be used as a barrier layer. And for instance, in comparison to PLA, they are far more biodegradable. So, but we are not experts in that. It was an example of microalgae.
Okay, thank you.
Q&A. Okay, and then we can go further to the third presentation if there's no more questions. But whoever wants to ask something from speakers, then it's possible to add it to the chat. And all the speakers are still here, so it's possible to ask from the previous presenters also. So the third presentation will be made by Tõnis Paara, who has 5 years of experience as the R&D specialist in Estiko-Plastar, which is one of the leading flexible packaging producers in the Baltics. He is also a 4th-year PhD student at the University of Tartu, material science, specializing in polymer barrier properties. So it's very good in the topic.
As said, my name is Tõnis Paara. Thank you for having me, and I'll give an overview of the eco-friendly packaging options that we have, so to say, from the industrial point of view that we use and that we can provide for our clients. Also some of the solutions that we do not offer for our clients, but that we have heard of or come into contact with. So first of all, in the sense of circular economy, this is the thing why we're talking about this subject in the first place, is that the European Commission has stated that all plastic packaging on the EU market will be recyclable by 2030. And regarding the biodegradable and compostable plastics that Dr. Kriipsalu talked about, I would put the emphasis over here on recyclable and circular economy. But of course, we will get back to that. So the idea is that from raw material, we get a full circle back to raw material. We produce it, use it, collect it, and recycle. This is the viewpoint that Estiko-Plastar shares with the European Commission, and this is what we recommend for all our clients. So we're not too keen on compostable solutions. So moving on, we can basically divide the eco-friendly packages into 2 sections. First of all, the end-of-life approach, which means biodegradability and compostability, or recyclability of the package. So the idea is that at the end of life of the package, what we're going to do with it. And this approach deals with the end of the life cycle. So after that, it will only become biomass or new product in the case of recyclability. And the other approach would be the raw material approach, so that we get the biobased raw material for production of plastic, or in most recent events, even mixed plastic waste. So this is the approach that we are more fond of, and we think this one is the really sustainable one. You can see the first picture of similar to the cup that Dr. Kriipsalu showed, ideally degrading them. And on the bottom, we can see that from sugarcane, you can produce polyethylene. Also, I'm very glad that Dr. Kriipsalu shares so many views with us. I'm gonna go quite briefly over this subject also. The oxo-degradable solutions, there are quite many producers of these kinds of additives for polymer materials. We have done some testing of our own many years ago when this subject was quite new and no one really understood that this oxo-degradation is not the solution, and if anything, it makes things even worse, because this means that the film breaks down into small particles and nothing eco-friendly about microplastics. Yeah, there's special additives that you add to regular polymer, and if the duration is not mentioned when it will biodegrade, that's always a red flag about any material. This is already banned in Spain, France, and Italy. The EU-wide ban that Dr. Kriipsalu said is coming in 2021. The last information that we have is that the ban was stopped by the oxo-degradable additives producers industry because they found some technicalities that papers that were prepared for the ban had some miscommunication about some terms. And there's also a good quote from Professor Tony Underwood from the University of Sydney, that it's not a solution to anything much unless we're happy to shift all plastic into particle-sized pieces, rather than plastic bag-sized plastic, because if the plastic remains in large quantities, then we can at least remove it quite sensibly from the environment. If it breaks down into really small pieces, there's basically no way of getting that out of the environment. And on the right, you can see the scheme of degradable plastic. So not every degradable plastic is biodegradable. Not every biodegradable plastic is compostable. So it's a really complicated issue, and I will talk a little bit more about biodegradability. So as Dr. Kriipsalu already explained, plastic processed into water, CO2, and biomass. So yeah, this applies to industrially compostable materials. There are really few facilities that accept biodegradable plastics, as also Dr. Kriipsalu said. And this requires very precisely controlled conditions, 90% biodegradation in 6 months at 58 degrees. So this means that it has to be a special reactor, not even the industrial composting units that we have in Estonia that do these in open air. And these are the most popular ones all over Europe, I think. Not too many composting sites have these reactors. And the probability that even if you have a compostable plastic package, that you sort it properly, it will probably never end up in the actual environment that it will biodegrade in. Okay, so industrial biodegradability is not really feasible anywhere. Let's talk about composting and home composting. There are very many different certification bodies. One of the most known is the VANCOT or VASOT, as they pronounce it, certification program. And this also requires completely ideal composting conditions. So if you think in our region that you will put this plastic into your compost bin and it will biodegrade, then yeah, maybe someday, but this means that your temperature in the composting heap has to be at 20 to 30 degrees, and it will compost it has to compost basically in 1 year. And I don't think any of our compost heaps have that kind of temperature for that kind of duration of time, so it will reasonably compost. Okay, so a little bit about the products that are available on the market. Many of these are quite popular. Many of our clients also ask from us to get these kinds of materials, but we always tell them basically the same story we're talking about here, that it's not really feasible, not really practiced anywhere. I think that in a reasonable sense that really plastic is biodegradable and becomes compost. But if they still require it, regardless of our information or recommendations, we are able to, offer it. So the most popular all over the world is PLA, or polylactic acid. This is also the filament that most 3D printers use, and advertise it as really, really eco-friendly and compostable and super good. In reality, of course, it's not. It's also industrially compostable, which means it will probably never be composted. This is a starch-based polymer. It has an extremely wide range of use. You can see some packages on the bottom there. You can use it to make film, to make plastic bags. You can make it into printed products or even transparent trays. So you can do flexible and rigid packaging. It's quite widely available. It's not too expensive, but it has a lot of different properties that make it difficult to use in regular packaging machinery. It's quite heat sensitive. It's quite stiff. It's really easy to tear. So many packages already have problems with these conditions. It has a very low oxygen barrier, but quite high water vapor barrier. So in the case of food products, I forgot to mention, Estiko is mostly dealing with the food industry. So oxygen barrier is really important for us. So in this case, if we would like to use it in some kind of food package, we would have to laminate or incorporate it with some kind of barrier material that would take away the small advantage of it being biodegradable. But one of the good things is that polylactic acid is recyclable, although only with itself. So when it goes into the regular plastic recycling stream, it's going to ruin the whole batch. So this should be sorted separately and recycled separately, which is also something I don't think is happening anywhere in the world. There is just not enough of this material to justify a separate recycling facility. So too far. Another material is PBS, or polybutylene succinate, which is industrially compostable. This is also quite widely used, and a few companies have started to promote it in the recent years. This could be both fossil and bio-based. It can be also used both for flexible and rigid packaging. This is quite expensive, not very widely available, but this has a lot of good properties as being heat resistant, but also it has a low water vapor barrier and a low oxygen barrier. So it's again not the best material to use for example, food packaging or moisture sensitive packaging. And this basically isn't even recyclable on its own. So yeah, again, nothing much to do with this one. It's mostly used for inner liner or paper cups to make them industrially compostable. And this is the material that the last presenter talked about, the PHA. This is also bio-based. It's very well compostable industrially, both in home and marine environments. And this can also be used for flexible and rigid packaging both. This is also quite expensive, and it doesn't really have widespread use at the moment. You can see on the bottom left there that the chips package is a project in work. They hope to bring it onto the market I think within a year or something. Again, something that's in my mind a little bit greenwashing, because this sounds good, but as we heard, industrial composting or composting on its own isn't really something we should aspire to. The material is waterproof. It has a mediocre oxygen barrier, so this can be used for food packaging, but the minus side is that it's not recyclable. So again, something that we as a packaging industry converter really are not going to look into. Some other home compostable materials is cellulose-based films, which is basically cellophane. It's really similar to polypropylene. This is also something that we produce for our clients, even though we don't recommend it, we could still offer it. This is also bio-based, so cellulose-based. It's mostly used for flexible packaging. This is very expensive since there are not too many, large producers that can supply this material in large quantities. But it has really good optical properties. It's shiny, glossy, very transparent, and they have very many different grades available. It can be metallized. It has a very high water vapor barrier and a high oxygen barrier on some grades. So it's basically a perfect substitute for polypropylene in the sense of flexible packaging, but the issue is again that it's not recyclable. The material is certified to be home compostable, but again, this probably won't happen. So a small overview of the end-of-life approach. Biodegradable solutions. There are really few materials that I would call really biodegradable, in the sense that if it got out to the environment somewhere, someone threw it under the bush, that it would biodegrade. There are some materials available, but basically the issue is they are very moisture sensitive, and the problem is that they will start to biodegrade at the moment they have been produced. So if we produce, for example, a roll of film, put it into our warehouse, it ends up at the client's packaging factory in a few weeks, and probably will stay there for a few weeks, then be packaged. It will get some moisture, heat, sun, UV during transport, and when it ends up on the client's home, it might already be like a little bit biodegraded, or the product that has been packaged is already compromised because the packaging itself did not protect the product. So it defies the whole point, and in that case there is the question, why even bother with a package? So another point, that it does not reach composting usually at all. People just throw it in the regular bin, and there's no reasonable way of sorting it out. And if biodegradable plastic goes into the regular recycling flow, this will ruin the whole batch of the regular plastic, because it does not melt like regular plastic. It will start to degrade, create pieces, and this will reduce the quality of the otherwise okay recycled plastic. About recyclable end of life, this means that if we can consider this as an option to thrive for, or to try to achieve, this means that we can still use conventional plastics, polyethylene, polypropylene, PET, for example. But the huge issue right now is that there aren't enough recycling facilities in the world. Very few exist, with some exceptions for example, PET, that drinking bottles are made of. For PET, the recycling stream has really been quite effective. In the case of Estonia, I think we collect some 95+% of our bottles, and all of them go to recycling. This is something that is really great and should be applied everywhere, I think, because PET in itself is a really good material that is easily recyclable and doesn't lose too much of its properties when recycled. Because usually the problem with recycled plastics is they lose them, and since they're polymers, the polymer chain gets shorter each time it has been recycled, and at the end of the 5th or 6th cycle, the properties have basically disappeared, and you have to use virgin clean plastic to substitute it. So usually they have been using somewhat more or less 30% of recycled plastic with 70% virgin plastic. Also, one issue with mechanically recycled plastic is that it is not allowed to use it in food packaging. Recycled plastic cannot be in contact with food products. So this is also one reason we don't use too much recycled plastic, and also the reason there isn't too many recyclers, because there's not enough market for the recycled material. About recycling also, one huge issue is that the waste has to be sorted according to materials. This is in the sense of mechanical recycling, because different polymers cannot be recycled properly together. For example, most I think popular food packaging structure is PET plus PE or polyethylene, and this cannot be recycled. So we would have to separate the two materials, and only then we can recycle it. In reality, nobody can or will separate them, and the whole package will be either landfilled or burned. Neither of those are two good solutions. There have been some developments, so we'll get to that later, but yeah, mechanical recycling isn't too feasible also in the sense of it being eco-friendly. There is just too much material that can't be separated and can't be recycled on the shelves of packaging today. When using recyclable or recycled materials, the client has to accept that the package appearance and properties will change. We have had many clients who demand recycled material for their packaging, but when we inform them that the package might start to smell differently, be more hazy or matte, then the interest has gone away quite quickly, because in the case of recycled material, when it's chopped up, melted again, and produced into a package again, the recycled material will give off a distinct smell, which is not too pleasant. It's not very strong, but it's still there. You can feel it, and you wouldn't want to package your, I don't know, cosmetic, some kind of good smelling perfume in a package that smells. Also, if we send some kind of, let's say, fish package that there has been a fish in it, it has been discarded, collected, sorted, and recycled, it still might have the fish smell to it. So it's quite difficult to, how to say, sell someone this recycled material that smells of fish. I don't think anyone would want any kind of package smelling like fish. But the recyclability approach is great in the sense that it complies with circular economy principles. It means that the product we once had will become a similar or maybe even the same in the case of PET, the same package again. So moving on to the approach that me, myself, and most of the packaging community approves most is the raw material approach. So the idea is to use source material that is not fossil oil but bio-based to get how to say, conventional packaging materials, for example, PE, PT, PP, or poly-PA, which is polyamide. PE is polyethylene, PET is polyethylene terephthalate, PP is polypropylene. So one of the bio-based, I think one of the most popular bio-based plastics in the world right now is green PE. You can see the logo on the bottom here. I'm green. This is a company from Brazil that uses sugarcane byproduct to produce bioethanol, from which they produce ethylene and then polyethylene. This raw material approach means that the end product is identical to fossil-based polymer, which means you don't have to do any changes in the handling of the material. You don't have to do any changes in producing the, for example, film from granules. You don't have to have any differences in the production cycle or recycling cycle. It's identical to fossil-based polymer. There are some downsides. It's quite expensive, almost or more than 2 times as expensive. Positive side is also that there are different grades for rigid packaging, flexible packaging, and it has all the same options as the conventional fossil-based polymer. One of the issues is also that it has that it uses basically arable land because they use sugarcane. Some people are against this green polyethylene because they say that the production of this material takes away the land that should otherwise be used for food. Braskem itself has denied this, saying that they use the side products or byproducts for sugar production, so no food how to say amounts is compromised. But still, some people don't believe them. We are more believing them than not believing them, knowing the technology. But also I agree that it's maybe not the best way to get bio-based material or renewable sourced material. And in the example of this green PE, they say that the PE has a negative carbon footprint of minus 3.09 kilograms of CO2 per 1 kilogram of PE produced. So basically they say that they capture 3 kilograms per each kilogram of PE produced, which is quite great achievement. It is also certified by some kind of certification body. I don't remember right now which one, but it's basically scientifically proven that it is so. So yeah, there are much more different suppliers of bio-based materials available. This one is the biggest one. This is something we also use and offer to our clients. Yeah, other suppliers do not have the amounts and the how to say transportation and the availability of the material in the scale that we could use. So we have been sticking to this one. Yeah, and depending on the biomass that is used, it can take away arable land from food production. So another way to have renewable source material is to use other kinds of biomass instead of food products, basically. One of the newest, and I think the most promising way of getting source material for polymer production is actually, yeah, not even bio-based, but mixed plastic waste. There is a factory in Belgium, I think, that is just starting up that uses mixed plastic waste, depolymerizes it. They get a special like pyrolysis oil from this material, and they use this oil as source material together with fossil oil to produce like polymers, polyethylene mostly. It's also the same. It has identical properties to the fossil-based polymer. It's very expensive, sadly, over 3 times as expensive as fossil-based, and it's not yet too widely available, since there are only a few companies that have started up the production. But hopefully soon there will be more, and the price will go down, and we will basically get the solution to all the problems we had without having to change everything about our package production and waste sorting, collecting, and recycling. So the idea is they take all this mixed plastic. It would be great if it would be sorted. The yield of the final pyrolysis oil would be greater, but basically it can work with all kinds of polymers. You just push them into an oven, pyrolyze them, get an oil, and use that to make polymers. Again, this is great in the sense it's recyclable, and this is basically chemical recycling, which is a solution to all our problems. It seems a little bit too good to be true, but there haven't been too many life cycle analysis or other studies that would confirm that it really is as good as they say. Another option that is really similar, uses pyrolysis, is using biomass to produce this pyrolysis oil. So basically pyrolysis is pushing the biomass into a huge oven, pumping out the oxygen, and basically degrading it at a high temperature without the excess of oxygen. So it won't burn, it will basically degrade. And this is used with tall oil, which is basically pine oil. I think it's in Sweden, maybe even, where they take these wood chippings that otherwise would be used for the pulp industry. They take these wood chippings and produce tall oil from it, and this tall oil is used for the production of polymers. So yeah, this is the newest advancement in eco-friendly packages that we've seen, and we have been looking into it for the few months, and hopefully this will be more widely used and available in the coming years. So these renewably sourced polymers need tracing, of course, otherwise it's just nice promises that all the companies are pushing out, and it could be just greenwashing like it is with most of the compostable materials. So there are different options. One is carbon testing, which is basically determination of the C14 isotope to determine which carbon is bio-based and which is fossil-based. This is used, for example, with the green polyethylene, the I'm green symbol you see. And the other one is a mass balance principle. This one is used for the pyrolysis oil solution usually. And since the determination of fossil-based and the bio-based carbon is a bit difficult, you have to test each batch. They have approached it differently by using this mass balance principle, which is the ISCC logo you see down there. You have to get the certificate that all your processes are properly done, and the idea is that when you produce the how to say green or eco-friendly polymer, you put in, let's say, 1 ton of this tall oil, which is bio-based pyrolysis oil. You put in like 9 tons of regular fossil-based oil, and you get 10 tons of final product. But how to determine which part of that 10 tons is bio, which is fossil-based? They basically use a mass balance that 1 ton of green material went in the reactor, and no more than 1 ton can come out of it. And this is followed throughout the whole production cycle up to the final client. So this works in the way that we buy 1 ton of this ISCC certified material, we process it, and we cannot sell more than 1 ton of this material. We have to take in account all the different losses in procedures, and we can sell the amount that we have left, because there is basically no way of determining it or keeping it separate. It comes as a regular material. We just know that one part of it is basically fictionally green. It's basically like you can buy a green seat on an airplane. If you pay a little bit more, they will basically say that your seat used biofuel, so it's more economically friendly. It seems a little bit silly, but in reality, it works. If more people use this biomaterial, more biomaterial will be used and will be available on the market. So, taking it all together, what to consider when you want to make your package sustainable. First of all, avoid packaging overall if possible. If you think that you should replace plastic with paper, maybe you can even do without the paper. Yeah, I have told this to many people that they say that, oh, we can't believe you, you're a packaging producer, you just want to sell more plastic. Well, that's not true. We don't want to sell more plastic. We just want to basically sell as little plastic as possible for the highest price, which is a little bit controversial, but in our sense, it works in the way that we don't want to sell more plastic. We want to sell smarter plastic. We want to sell more sustainable plastic, because this is our, how to say, market advantage, basically. So we don't need to over dimension our products. Also, something we tell all our clients is to reduce the thickness to minimum. Many of them still fight with this because they think that the client still wants the premium feel to their package and premium look. But we've tried to convince them otherwise, that if they can give out the message that this package is way more environmentally friendly, then this will have the same or better result than the premium feel or look of the package. Also, something to consider is to avoid multi-material structures. For example, PET plus PE, like I talked before, paper plus PE, because this takes away the good possibility of recycling the fossil-based plastic. If you can't use, if you have to use package, if you can't use bio-based package, then at least use one polymer-based packages if possible. In some cases, of course, it's not, but whenever possible, this should be used. To increase sortability at the waste collection factories or facilities, you should avoid black and metallized plastic, since they are often sorted by near-infrared lasers. These cannot detect most black or metallized plastic, so they will get sorted separately and will go into landfill or incineration. If possible, use packaging that is renewably sourced, hopefully soon then made from mixed plastic waste, which would be preferred. And as you can see on the bottom here, many people or companies use way too much packaging that it's just not necessary. I have a few slides more that show the difference of different packaging. So we have had huge, how to say, the plastic industry and the paper industry are basically going head to head, saying that which one is better. This information is basically from plastic packaging. I would say more plastic packaging supporter. There are not too many, how to say, researches that are not funded by either. So it's basically neck and neck, but you can see that in the sense of product to package ratio, there really is no competition to plastic. You can get the barrier properties, the lightness, and the price, water usage. Everything is in favor of the flexible packaging. Me myself, I'm also a huge believer in plastics because they really are an amazing material. We can do so much with so little material. We can protect the package in basically an ideal way without using over, I don't know, 10 grams of material. So you can see that even if the paper is more easily recyclable, in the sense of transport and water usage, plastic packaging just has a huge advantage. And this is a comparison we did ourselves. This is actually not for say advertising purposes. We just really wanted to know ourselves. We bought a few shopping bags, weighed them, and using I would say pretty unbiased data from the Danish Environmental Protection Agency, we saw that the amount of material used and the CO2 emissions per package, or basically any parameter here, water used during production or energy used during production, is heavily in the side of polyethylene, or even better in the case of renewably sourced polyethylene. On the right, the green PE is the PE made from sugarcane. You can see that the CO2 emissions per package is, well, in the minuses. As for paper, it's plus 200. So the difference is quite huge. So yeah, that's mostly it. This is our slogan: think big, act green. Thank you.
Thank you very much. It was very interesting presentation, and very much loaded with information. And I wanted to let everyone know that are still here that it's possible to get these presentations afterwards. We will send you it to your email address. And we have some more questions. Maybe you, Tõnis, would like to answer some of them.
Yeah, I will look these up. Starting from Müller, Marcus, yeah, mechanical thinking. Yeah, the Marcus Mühlenhoff has a really good point. Yeah, basically only monomaterial is mechanically recyclable. Well, polyethylene and polypropylene are, in some sense, recyclable together, but the result is not as good as they would be when they would be recycled separately. Yeah, PET PE would go in incineration, mostly landfill probably. Chemical recycling would do, but also the material you gain from it is still lower than when you would use a monomaterial. For Sanaben, Otman, et Alolu, the recyclable means that PET can be recycled, but it cannot be used as a food packaging anymore. Well, with PET, it's a little bit different. I know that for bottles, it is possible for a used PET bottle to be recycled and reused as a food, like beverage bottle again. But this is also really heavily regulated, and there aren't too many companies that can do this. I think the trademark was clean bottle or something like that. I don't remember quite exactly. But in the sense of PET, it is possible. In the sense of polyethylene, polypropylene, not really. In the law, it states that it is possible to use them in a food package when there is a functional barrier layer between the recycled material and the food product. But we have investigated this, we can produce it, but in reality, the price goes so high. since we have to use the barrier layer, that it's just economically not feasible, and I don't think it's also economically or eco in the sense of eco-friendliness. It doesn't have too much point because you add a material that otherwise wouldn't be there to protect the food from the recycled material.
Okay, thank you for the thorough answer. And I think if we don't have any more questions.
There was one other
then-
question.
Yes.
On carbon sequestration claims of the polyethylene. Maybe I can just ask that myself. I heard in your presentation you mentioned something about more uptake than emissions in the supply chain. So I just wanted some more information on that. A link, if possible, to any studies that you know of.
Yeah, I can share you their link that they have on their homepage, I think, where they say that this they basically bond 3 kilograms per kilogram produced. Did you mean this about
Yes, exactly. That was the one. And I was just curious, could you just tell us a little bit more about the sourcing of that plastic? Do you know if it's a fossil-based or a biomaterial or?
Yeah, no, that's a biomaterial. I think it's basically sugarcane. They produce they produce ethanol from it, from a byproduct. I think it was called bagasse. They actually produce sugar from sugarcane. They have this bagasse that is left over. This is used to make bioethanol, and that ethanol is used to make ethylene. They're the biggest producer of this bio-based polyethylene in the world, I think. It's used quite a lot, but there is a lot of controversy around their company also. Some of our clients in Europe have declined using that because of some issues with the Brazilian government, saying that there were some problems with some kind of can't remember the word in English, paying somebody off basically. But this is up to debate for now. There might be, but in my opinion, it is better than fossil fuel in the sense that it makes sense that sugarcane captures the CO2. We basically lock this into polyethylene, and this polyethylene continues in the regular polyethylene stream in recycling and everything. So it makes sense to me. But
it definitely makes sense. From a life cycle perspective, I can say a word on this because I work with these issues. I've seen very few actually peer-reviewed studies that show in a fair way that there is carbon sequestration taking place in any bioplastic product. The main reason for that is because the emissions of the supply chain processes end up exceeding the carbon that is uptaken by the biomass initially. And when you account for transportation across the world, sometimes, especially from Brazil to Europe, I would doubt any claim that says that the carbon footprint could be negative, taking in a life cycle perspective. Though when you talk about all of these byproducts, there could be some arguments for reducing emissions there as well, that the ethanol is offsetting the use of other fossil products and so on. But this is a complicated world, which is why I wanted to know if there was any further reading that you could link to us so that we can find out.
Yeah, probably the reading that I can link right now is probably heavily in favor of them, since they're the one that published it, have like advertised this to us. And as you said about this whole life cycle analysis, there are so few materials available that really are like unbiased for any kind of supply chain or production of any kind of material. It's terrible to find information that you can really believe. And me also, I'm not saying that this Braskem's material is 100% everything is okay, but this is the info that I have gotten a hold of. So yeah, I'm quite skeptical about most of these. Also, actually, about the chemical recycling. In theory, it sounds great in the sense of material, but if we consider the carbon emissions, then I'm not too sure, because you put a huge amount of energy into it to make it back into a basically polymer soup, and then put more energy to produce it back into a polymer. So it's how you look at it. Do you look at the CO2 cycle, or do you look at the material cycle, but so that we don't throw anything into the ground? So there are so many different aspects that you have to consider. I think it's basically impossible to say which is best or which is greatest. It depends on where you're looking at. Yeah.
So thank you very much for participating, and hope it was useful for you. And bye. See you.
Thank you.